Those of you on the live stream, just doing a quick audio test. Can you guys hear me okay? Please let me know in the chat room. Let me know if it's too loud or too not loud or crackling or anything like that. Awesome, thank you. Well, hello everybody. Welcome to another live stream from practicalnetworking.net. This is, if I'm counting it right, this is the 4th live stream I've ever done. I'm excited to do another live stream to demo teach the routers curriculum from the Networking Fundamentals video series. If everything's coming through okay, which it's looking like from what I can see on my side, go ahead and mention something in the chat room. Let me know that you can hear me okay, you can see me okay, and this live stream is starting off well, I hope. Cool. Well, glad to hear it. I just put a poll in the chat room. Go ahead and answer that. Let me know if you guys have seen all the videos so far in the Networking Fundamentals series. The plan for today is simply to pick up where the series left off as we discuss routers. I don't have all too much insofar as announcements. The plan is going to be, we're going to run through the lesson content. I'll do some quick Q&A in the Discord after the lecture portion is over. If you guys have any questions for anything, definitely feel free to throw them in the chat room. The chat room is pretty delayed, so I won't be able to answer them live, but I will definitely stop every 5 to 10 minutes or so to make sure I haven't missed any questions, and I'll come back and get to them. That said, the purpose of this live stream is to, again, demo teach the routers curriculum, which will one day become, published and edited and polished videos that I'll add to the end of the actual Networking Fundamentals series. And with that in mind, I guess we can just get right into it. Cool, so it seems most of you actually have not seen the majority of the Networking Fundamentals series. That's totally okay. I'm glad you joined nonetheless. In that series, I pick apart everything you really need to understand in order to really know how data moves through a network. Yeah, so let's get right into it. Okay, so for those of you that haven't seen the video series, I would definitely highly recommend going back and watching the other videos in this series. In those videos, we went through 4 lessons so far in the series. This is actually the 5th lesson in the series. In the first lesson of the series, we picked apart the ideas of networks. We picked apart IP addresses. We picked apart hosts and clients and servers and what all that meant. But essentially, we identified a network as a logical grouping of hosts, meaning these 3 are a logical grouping of similar hosts, and they communicate to each other through the switch. Same thing over here, they're a logical grouping of hosts. And we picked apart that the idea of routing is simply the process of moving data from one network to the next. And a router then, as we are going to be picking apart today, is merely a device whose primary purpose is routing. Now, the reason it's important to understand it that way is there are many types of devices out there you're going to look at. There's load balancers, there's access points, there's layer 3 switches, there's proxies, forward proxies, reverse proxies. All of them, or no, I shouldn't say all of them, most of them are going to claim to do routing. So as we go through this lesson, we're going to be focusing on a router, the actual device whose primary purpose is a router. But any of those other devices that also claim to do routing or layer 3 processing are also going to be following all the rules that we're going to be discussing in this lesson. So make sure we understand that routing is the process of moving data between networks, and a router is simply a device whose primary purpose is routing. In any case, we picked all that apart in lesson 1 and a bunch more. Then we moved on to lesson 2, where we discussed the OSI model. We discussed the idea of, for a host to get data from one side, from this host to over here, it's going to generate the data that it needs to send. It's going to add a layer 3 header, which is going to handle the end-to-end delivery. That layer 3 header is going to have a source of that IP address and a destination of that IP address. Then a new layer 2 header will be added to account for every single hop on the path between the 2 endpoints. All this we picked apart in great detail in lesson 2. when we discussed the OSI model. So definitely, if this is unfamiliar to you, definitely go back and check out that lesson. Then in lesson 3, we picked apart the idea of hosts, and we identified and illustrated everything hosts do when they're speaking to other hosts. We start off talking about hosts speaking to other hosts in the same network. We illustrated every single step that's required for host A to speak to host B. And we identified that those steps are the same regardless of how host A or host B are connected, whether they have one switch in between them or two switches in between them or whatever. Then we identified everything or illustrated everything that happens for a host to speak to another host on a foreign network. Notice it's on the other side of a router. In doing so, we showed you really how a host speaks to anything on the internet, regardless of how it's actually connected. This let us show you and explain the purpose of ARP and how ARP maps a layer 3 address to a layer 2 address, and how significant that is, in the processing of data on the internet. Now, all of this we picked apart in great detail in the first 3 videos of the Networking Fundamentals course. Now, not on this list is lesson 4, where we picked apart the switch's role in this. We talked through everything that a switch does to facilitate communication within a network. In this lesson, we're going to be looking at routers. That's going to be the purpose of what we're going to discuss today. With that in mind, let's get right into it. Oops. So, here are 2 hosts, and both of these hosts are sitting on the 10.0.44 network. Host D has the IP address 10.0.44.3, and host A has the IP address 10.0.44.9. Now, both of these hosts are connected to the network using their NIC, and their NIC is identified by a MAC address. Here I'm just showing you the first 4 digits of the MAC address simply to conserve screen real estate. But normally a MAC address would be 12 hex digits long. Now, routers are also connected to networks just like hosts. And the reason, or I should say, what makes host D and host A connected to this network is the fact that they have an IP address in that network. Well, in the same way, a router connected to a network also has to have an IP address. And whatever the wire actually plugs into is also going to have a MAC address. So you'll see the router, just like the host, also has an IP address and a MAC address. Now, normally, everything on this network would be interconnected via a switch. Notice everything is plugged in via the switch over here in the middle. But since we discussed switches in the last lesson, I'm going to leave switches out of this lesson simply to reduce the variables. So for the purpose of this lesson, everything in this box or touching this box is connected via switch, but we're going to ignore the switch's role in all this for now. Now, since routers are very similar to hosts insofar as what we've described so far, meaning they need to have an IP address and a MAC address just like hosts have an IP address and a MAC address. This begs the question, how is a router actually different from a host? Well, my favorite definition of this actually comes from the IPv6 RFC. Now, if you're unfamiliar with RFCs, they're essentially the documents that all internet specifications are written in. If you're ever having a nerd argument with someone about how something on the internet works, if you can quote the RFC, that's pretty much the trump card. You win that argument because the RFCs are essentially the Bible for network engineer. In any case, the IPv6 RFC has this for terminology defining node, router, and host. Cool, so a node is simply anything that implements IPv6, but this also translates to IPv4. So when you hear the term node, that's anything with an IP address. A router, then, is simply a node that also forwards packets not addressed to itself. That's how a router and a host are different, because a host does not. Meaning, if host D somehow magically receives a packet with a destination IP address of, say, 8.8.8.8, host D is just going to drop that packet. It's like, oh, this isn't for me, I don't care. Whereas if the router receives a packet with a destination IP address of 8.8.8.8, the router is going to see what it can do to get that packet to that destination. That is the difference of a router and a host. Now, cool. So that's the difference. So let's continue talking about it. Now, In order to forward packets not destined to itself, we're going to need other routers that the network is connected to. So here, R1 was connected to the 10.044 network. Now we're going to add a new network, the 10.055 network, and we're going to connect R1 to that network. Just like over here with a 10.044 network, R1 had an IP address and a MAC address for the interface where that network was plugged into. Well, in order to connect R1 to this network, we're going to again have to have an IP address and a MAC address. I missed an animation. There's something that's supposed to appear over here. Oh well, we'll fix that later. This IP address and MAC address that a router has to happen for every single network that a router is connected to. In fact, that is the definition of a router being connected to a network, is it has an IP address on that network. Now, in order to do this forwarding packets not destined to itself, the router is going to have to maintain a map of all the networks it knows about so that it knows where to send packets. That map is what's known as the routing table. We briefly touched on the routing table in lesson 1. A routing table is a map of all the networks that a router knows about. At this point in time, for R1 only knows of 2 different networks, and the routing table is going to look something like this. It's going to say, for anything that R1 receives with a destination IP address of 10.055. whatever, that packet should be sent via the left interface. Normally, the router interface would be something like FA01 or Gig01 or something like ETH0, ETH1, etc., etc. For simplicity, I'm just going to call the interfaces left and right. And then the other entry you would see in R1's routing table at the moment would be for anything destined to 10.044. whatever, send it out the right interface. This routing table is what the router is going to use anytime it gets a packet. Meaning if host B sends a packet to R1 with a destination IP address of 10.044.9, host A's IP address, the router is going to take a look at its routing table to determine that that packet should go out the right interface. And it would be the same thing if host D decides to send a packet to the router with a destination IP address of 10.055.8. The router is going to look at the routing table to determine that that should go out the left interface. So that's the idea behind a routing table. And that's actually a good place for the first pause for questions. If all this is sitting pretty well, go ahead and mention something in the chat room. And if you have any questions, definitely type them to the chat room, and I'm happy to answer them. The main takeaway so far is understanding that routers have IP addresses and MAC addresses, and the purpose and definition of a routing table. If that all makes sense, go ahead and mention something in the chat room, please. Cool. Thank you, Tony. Appreciate it. Cool. I like it, Tony. Yes. Great question, Jewel. I don't know if I'm saying you're right, but no, they're not any different. They're just going to be using v6 addresses, but for the most part, they're going to work the same. Okay, so let's go a little bit further. This routing table is actually a large part of what anybody in the networking field is going to concern themselves with. So we're going to speak a little bit more about routing tables. The routing table can be populated via 3 methods. The first method is actually the method we just discussed, is what's known as directly connected routes. So here are, any network that a router is actually connected to, the router is going to learn a directly connected route for. For example, here is R1's routing table. And what you'll see is this routing table is actually the same one we had a moment ago. A moment ago right there. This routing table indicates 2 directly connected routes. That's what the DC stands for. And the directly connected routes indicate that the 10.055 network is out the left interface and the 10.044 network is out the right interface. So really, we've already understood directly connected routes. They exist for any network that a router is attached to. Okay, so let's add another network to our topology. Here is the 10.0.66 network, and we're going to connect that network via R2 to everything that we've already discussed so far. Well, notice R2 at the moment doesn't have any IP addresses or MAC addresses. What this tells us is that R2 isn't actually plugged into these networks yet. So let's go ahead and plug in R2 one at a time. So first we're going to plug R2 into the 10.0.55 network. And what that means is we're going to connect the physical cable to the switch, or maybe it's via Wi-Fi or whatever the case. Then we're going to configure an IP address on R2. In this case, R2 has the IP address 10.0.55.2. The moment we configure the IP address, R2 is going to learn something in its routing table. It's going to learn that the 10.0.55 network exists out the right interface of R2. Then, as soon as we configure an IP address on the other interface of R2, we'll configure the 10.0.66.2 IP address. Instantly, R2 is going to learn of a new directly connected route that the 10.0.66 network exists out the left interface of R2. Notice both R2 and R1 have independent routing tables. Each router is going to maintain their own routing table, their own map of every network that they know about. Cool. Now, what happens if host C sends a packet to R2 with the destination IP address of 10.0.55.8, R2 is going to be like, okay, do I know about the 10.55 network? If so, I'm going to send it out the appropriate internet. The appropriate interface, rather. But if host C sends something to host A's IP address, 10.0.44.9, when that packet arrives on R2, R2 is going to take a look at its routing table and realize it doesn't know about the 10.0.44 network. Well, when a router receives a packet that it doesn't know how to deliver, the only option that the router has is to drop that packet. From the perspective of each router, the routing table is a map of every network that exists. So at this point in time, R2 doesn't know that 10.0.44 exists. Again, it's only directly connected to these two networks. In the same way, R1 doesn't know that the 10.0.66 network exists. It's only connected to these two networks. So while directly connected is a great starting point to discuss the routing table, it definitely isn't the only option for how a routing table is populated from a router. There are two other methods we're going to discuss. The first is what's known as static routes. A static route occurs anytime an administrator manually provides a route to the router. Meaning, I can jump on R2 and I can tell R2 about the existence of the 10.0.44 network. I can tell R2, listen, anytime you're trying to deliver something to 10.0.44.anything, send it to 10.0.55.1, which is R1's IP address. Now, if host C sends something to host A, R2 will know to send that packet to router 1, and then when router 1 gets it, router 1 knows of the 10.0.44 network and will know to send that packet out the right interface. But we also have to consider the response traffic. If host A tries to respond back to host C, host A is going to be sending a packet to router 1 with a destination IP address of 10.0.66.7. And at the moment, router 1 does not know of the 10.0.66 network. Well, just like I told R2 of the 10.0.44 network, I'm also going to tell R1 using a static route of the 10.0.66 network. In this case, I'm going to tell R1 that anytime it needs to get to the 10.0.66 network, it needs to send that packet to R2's interface IP address, 10.0.55.2. Now, host C and host A can speak to each other through these routers, because each router knows of all the networks in this topology. So that's the idea behind a static route. Now, so there's a question in chat, when are routing tables cleared out? They shouldn't be unless by admin override. Ideally, a routing table is populated and knows of all the networks it needs to deliver traffic for, and set in stone unless new networks appear or are added or are discovered. Which will actually tie into the next question. Cool. So I said there are 3 methods, and so far we've only talked about 2. So let's talk about this third one. The third method of populating a routing table is what's known as dynamic routes. Dynamic routes are interesting. Just like a static route was an administrator telling the router about networks it doesn't know about, dynamic routes involves the routers automatically talking to each other and telling each other about the networks they know so that they can tell each other about networks they might not know about. So if we clear out our routing table, the static entries in our routing table, in dynamic routing, R2 will say something like, hey R1, I know about the 10.066 and the 10.055 network. And then R1 will be like, oh cool, well I already know about 10.055, but what can you tell me about 10.066? Then R1, oops, I did that backward. Then R1 will be like, sweet, I'm gonna send anything about anything that's destined to a 10.066 network to you. In the same way, R1 will have shared information about the networks that R1 knows about to R2, and then R2 can learn that anything it sends to R1, rather anything it needs to send to the 10.044 network will be sent to R1. Yeah, great question, Tony. Actually, that's kind of the next bullet. So there's actually a bunch of different dynamic routing protocols. So if you've heard RIP or OSPF or BGP or AGRP or ISIS, all of those are dynamic routing protocols. All of them are simply different strategies for how that router-to-router communication is going to happen, in which they share information about the networks. They all differ insofar as how often communication happens, how that communication happens, what sort of messaging structure they use, what's included in the information, what happens when there's a failure, what happens when, how much control you have over what is shared, etc., etc. So that's what a dynamic routing protocol is. Now, each of these, they're all generally pretty fascinating and pretty interesting, but they're well outside the scope of what we're going to try to do with this module. I just wanted to define them for you right now. So that is dynamic routing. Now, I do want to quickly point out, notice that the actual content of the route is identical to what was learned with a static route. In both cases, R1 simply knows that the 10.066 goes to 10.0.552. Going back to our dynamic analogy, 10.066 still goes to 10.0.552. So the actual content of the route, insofar as static and dynamic, is pretty much the same. It's just about, did an admin provide it, or was it auto-magically learned using one of these dynamic routing protocols? Cool. So that is the idea behind the routing table and the 3 methods of learning entries inside the routing table. A large part of any sort of networking career involves managing, if you will, the routing table of different routers, or ensuring that the routers are in a position where they can learn about the networks that they need to route for. Jewel, to your question, I would say VLANs are somewhat independent concepts from routing. If you go to pracnet.net/VLANs, you'll see an article that picks apart what VLANs are. There's also a video on YouTube on my channel. Seems my camera froze, but it looks like audio is still coming through okay. Can you guys still hear me okay? Strange. Don't know why my camera froze. We'll just turn it off for a while and see what happens. Okay, so let's press on. Okay, so what we're going to be doing in a moment is I'm going to show you every single step that's going to occur for host A to send a packet through R1 to get to host B. Then we'll do the same thing, but we're going to show you every single step for host A to get a packet through R1 and R2 to host C. we're going to show you each of these to really nail down the router's role in internet communication. But before I do that, there's one more idea I want to leave you with. In Lesson 1 of the Networking Fundamentals series, we showed you this topology. We use this topology to explain different networks and IP addresses and how they're set up in a hierarchy. Notice the Acme Corporation owns everything that starts with 10 dot whatever. And the Acme Corporation has two offices, one in New York, one in Tokyo. Tokyo owns everything that starts with 10.40, which is a subset of Acme Corporation. And New York owns everything that starts with 10.20, which is again a subset of the Acme Corporation. And then each of those has teams within the physical offices that each have a subset of the IP space of the physical office. The sales team has 1040.55. Engineering has 1040.66, and so on. In Lesson 1, I told you that the routers are actually what's facilitating that hierarchy. They are the ones who are creating the hierarchy in the IP assignment for this particular topology. Now that's an important point because these routers are set up in a hierarchy very intentional. They're set up that way to facilitate scale. Down here, our routers are set up in a line, linearly, right? Notice it's a straight line. Whereas over here, they're actually set up in a hierarchy as you would see in real life. The reason that's better is that this topology will scale much easier. For example, let's say the Tokyo offices adds 3 more teams: the accounting team, the help desk, and the operations. Each of those teams is going to have new IP space within the Tokyo assigned IP prefix. Well, let's just say these are not assigned in a hierarchy. Let's just say these are now assigned linearly. What ends up happening is that for the sales team to speak to the marketing team, they're only crossing 3 routers. But for the sales team to speak to operations, they have to cross 6 routers, which means they're going to have different available bandwidth and throughput speaking to different teams simply based upon where they are in a line. Moreover, the sales team speaking to the internet is going to be much quicker than any of the teams that are added later on as you grow. So that's why typically routers are programmed in a hierarchy to make things more consistent insofar as network design. With this hierarchy over here, now when the sales team wants to speak to marketing, it's simply going to go to the sales router, to the aggregation router, to the marketing router, and then to a host in the marketing team. And notice in that we only crossed 3 routers. It'll be the same if the sales team wants to speak to operations. It'll hit the sales router, the aggregation router, the operations router, and then the host in the operations. Notice you have much more consistent scaling of your network. Cool, so that is hierarchy. Now, in all cases, the routing table of every single router in this topology needs to be accounted for. For instance, take this router right here. This router needs to know of the sales, the 102055, 102066, 102077 network, and it needs to know of the 104055, 104066, and 1040.77 networks, as well as all the networks out on the internet. Well, because of this hierarchy, you can actually do what's called route summarization. Instead of telling this router that, to get to 104055, go this way. To get to 104066, go this way. To get to 104077, this way. Instead of telling that router 3 different things, I can simply tell that router, listen, to get to anything 10.40, go this way. And that'll automatically account for all the networks that currently exist, and any additional network in the 1040 IP space that are going to exist in the future. That's the idea behind route summarization, and that's only possible if your IP space and your routers are deployed in a hierarchy. Moreover, you can do what's known as the ultimate summary by creating a route for this address and mask right there. 0.0.0.0/0 is known as the default route. What that does is it tells a router to get to anything, go a particular direction. Consider this router right here. This router is directly attached to the marketing network. It's going to then need a static route or a dynamic route for every other network in the topology to include the internet. But notice in all cases, the router's only way out of the network is to the aggregation router. So instead of flooding this router's routing table with a bunch of entries, why not simply say, listen, to get to anything else, go this way. That's what this summary route would do. That's what's known as a default route. Conceptually, it's actually very similar to a host's default gateway. Just like a host would use a default gateway to get to anything on a forward network, you can tell a router, you can rather provide a router a default route, which is a route for this address and mask, which will tell the router how to get to any other IP address it's trying to get to. And this router right here, really any of these smaller routers on the outsides of this topology are perfect candidates for default routes. Great question, Tony. That's something, so if you're doing static routing, the administrator would do it manually. If you're doing dynamic routing, it can be programmed, depending on which routing protocol you're using, it can be programmed or configured to also do route summarization. So both is sort of the answer to your question. Route summaries and default routes can be learned either statically or with a dynamic route. So if I tell this router over here to get to everything, go over here, that's a static route. But if this router automatically tells that router to get to anything, go to it, then it's a dynamic route. So it's all about how the route was learned. Cool. So that's actually it for the first part of this lesson. The first part, the main points were routers have IP addresses and MAC addresses for every network that they connect to. Routers maintain routing tables, which are populated via these three methods, and a routing table includes every network that a router knows about. And finally, that routers are connected in a hierarchy to facilitate route summarization and or default routes. Cool. The next part of this lesson is going to now be picking apart everything that happens for host A to speak to host B and for host A to speak to host C. We're going to show you every step for that to occur. But again, this is actually a good place for a quick little check-in with everybody. If you're following everything so far and all of these key points make sense, go ahead and mention something in the chat room. Let me know that this is all settling well and you are ready for the next part. Cool, glad to hear it, Tony. Glad to hear it, Snakebite. Jules, so the firewall is also sort of a separate concept. If your firewall is also doing routing, then everything we just discussed and so far as routers also applies to the firewall. But a firewall isn't necessarily going to prevent the existence of routes or anything like that. Cool. So let's press on. Okay, so this is going to be a second video on YouTube. All that first part was really going to be the first video, part 1. Now we're going to get into part 2, and in part 2 is where we'll be actually discussing everything that occurs for packets to get from host A to host B. Now in part 1, again, the things to keep in mind is that routers have IP addresses and MAC addresses for every single network that they are connected to. Moreover, routers are going to have routing tables, which are a map of every network that they exist. Again, all of this is stuff we picked apart in the first part of this lesson. You guys just sat through that, so we're not going to spend too much time reviewing it. But here is a representation of R1's routing table, and here is a representation of R2's routing table. Notice in both cases, the directly connected routes are listed, and in both routers' cases, a static route was provided for the one network that it wasn't directly connected to. So yes, all this we covered in part 1. Sweet. What we didn't explicitly call out in part 1 is that not only do routers have routing tables, but routers also have ARP tables. Back in lesson 1 of this series, I told you everything with an IP address also has an ARP table. Well, notice each of the routers have IP addresses, which means they also have ARP tables. That was interesting. Which means they also have ARP tables. Notice R1's ARP table is going to have a layer 3 address, an IP address, to MAC address mapping for every node that R1 that is in a directly attached network for R1. So R1 has one other node in the 1044 network, that's host A, and there's a ARP mapping for host A. On the 10055 network, there are two nodes, R2 and host B, and R1 has an ARP mapping for each of those nodes. It's the same way for R2. R2 also has an ARP mapping for all the nodes in directly connected networks. For the 10066 network, there's only one other node, that's host C. And then for the 1055 network, the other nodes would be host B and the router. Now, here's the key about the ARP table. The ARP table actually starts out empty. Meaning, at the beginning, before any data has flown through this network, both R1 and R2's ARP tables are empty, and they're going to be populated as necessary live with traffic. That's not the case with the routing table. The routing table has to be populated before the router receives any data. Remember, if a router receives something that it doesn't know how to deliver, the router is going to drop that packet. There isn't a automagic process that it's triggered to learn about other networks. ARP is not that way. With ARP, if the router is trying to deliver something that it doesn't know a MAC address for, it's just going to do ARP to figure out the MAC address. So ARP tables start out empty, and they are populated live with network traffic, and you're going to see it as we step through all the steps necessary for host A to speak to host B. Okay, so let's get to it. Cool, sweet. All right, so for host A to send data to, this illustration is going to start with the idea that host A has some data it needs to send to host B. Now, you and I, as the network admins, we don't know, nor do we care what that data is. It's just a bunch of ones and zeros that we know need to be delivered to host B. Or rather, that host A is going to tell us to deliver to host B. Host A will tell us that by adding a layer 3 header to that packet. That layer 3 packet is going to have a source IP address of host A and a destination IP address of host B. That's what's going to identify the endpoints of this conversation, the end-to-end delivery. Next, host A needs to throw a layer 2 header on there to get the packet to the router. But at the moment, host A cannot construct the layer 2 header because host A doesn't know router 1's MAC address. Host A theoretically will have been configured with a default gateway, telling host A to get to a foreign network, use the IP address 10044.1. But since we're illustrating as if host A has never spoken before, at the moment, host A doesn't have the router's MAC address, so it cannot create the layer 2 header necessary to get the packet there. Now, all of this we picked apart in the host-to-host communication lesson, which was lesson 3. So if you want more details on how host A speaks through a router, definitely check out that lesson. In any case, host A is going to have to go through ARP, so it's going to send out an ARP request. That ARP request is going to ask for the MAC address that correlates to the IP address of R1, 10044.1. And notice the ARP request also includes the mapping for host A. It includes its own IP address and MAC in the ARP request. That's going to get to R1. R1 will get it, and that'll allow R1 to populate its ARP entry with the mapping for host A, the person that sent the ARP request. Notice R1 has an entry for the IP address 10044.9 that maps to the MAC address A9A9. Then R1 is going to send the ARP response. That ARP response is going to be R1's mapping, the IP address 10044.1 maps to the MAC address EEE1. That'll get to host A, and then host A will populate its ARP entry with the MAC address for 10044.1, R1's IP address. Now on this illustration, we don't see host A's ARP table. we're just going to be focusing on the ARP entries for R1 and R2. In any case, host A now has what it needs in order to properly create a layer 2 header, which will take this packet from host A to R1. Once that gets to R1, R1 is going to discard the layer 2 header. The whole purpose of that header was simply to get the packet from host A to R1. Since it did so successfully, that header can be thrown away. Now, R1 is going to look up the destination IP address in its routing table. It's going to try and see if it knows how to deliver a packet to 10.0.5.5. Well, it has an entry for the 10.0.5.5 network. It knows that needs to be sent, rather that packet needs to go out the left interface of R1. Cool, so to answer the question in the chat, Surendra, we talked in the first part of this lesson, we discussed that there would be a switch connected, but since we are just talking about routers in this lesson, we are removing the switch to limit the variables. If you want to understand how switching works, definitely check out lesson 4 of the Networking Fundamentals series. I will post a link in the description, or it should be the first or second page on my, first or second post on my blog, practicalnetworking.net. And Tony, switches don't actually have MAC address. Sorry, don't actually have ARP tables. Just only devices that have IP addresses. Cool. Sure. All right, so coming back to it. So R1 is going to look up, rather determine, that this packet needs to go out this interface. But moreover, R1 knows that it's actually delivering this packet to its final destination. It knows this because the routing table entry is directly connected. What that means is the person that is being spoken to is in the network that is directly connected to R1, which means R1 needs to create a layer 2 header that correlates to the IP address 10.0.5.5.8. But the problem is at the moment, R1 doesn't have a MAC address for the IP address 10.0.5.5.8. So once again, R1 is going to have to do ARP. It's going to send out an ARP request for the IP address 10.0.5.5.8, the one that correlates to the destination IP address of the packet. That is, again, going to look like this. It's going to be sent out to everybody on that network. This router is going to get it and ignore it since it's not pertinent to that router. Host B is going to get it. Host B will learn about the ARP mapping for the router, and then host B will generate a response. In the response will be the ARP mapping that the router was trying to learn about. That'll then get punted to R1. R1 will then learn an entry in its ARP table saying that 10.0.5.5.8 maps the MAC address B8B8, and that'll allow R1 to create a layer 2 header, which will get this packet to host B. That will then get sent to host B, where host B will finally receive the data. Now that host B has received the data, it's going to discard the layer 2 header. Again, the purpose of that header was simply to get this information from here to here. Then host B is going to discard the layer 3 header. Again, the purpose of that header was to get this data from here to here. And finally, host B will receive the data. All of that is what's involved to get information from host A through the router to host B. For sure, Tony, I'll post a link shortly. Now we're going to step through everything that happens for B to respond. But what you'll find is that since most of the ARP entries have already been populated, that's going to go much quicker. Host B has some data to send back to host A. This is the response, and again, as the network admins, it's just a bunch of ones and zeros. We don't really know what's inside. Host B will throw a layer 3 header on there. That layer 3 header is going to have the source IP address of host B, and the destination IP address of who it's trying to speak to, in this case host A. Then host B, since it has the ARP mapping of the router, is going to construct a layer 2 header. That layer 2 header is what will allow this packet to be delivered to the router. Once that gets to the router is going to discard the layer 2 header and then look up in the routing table how to deliver a packet to 10.044.9. From the router's perspective, it doesn't know that those two packets are linked, that is the response of the first packet. Routers make their decision on a packet by packet, from a packet by packet perspective. Meaning, a new packet just showed up with a destination IP address 10.044.9. The router is going to take a look at its routing table to see if it knows how to deliver anything to the 10.044 network. In this case, it does. This needs to be sent out the right interface. And since R1 has a MAC address mapping for the 10.044.9 IP address, it can create the layer 2 header, which will take this packet to host A. That will then allow the router to send the packet to host A. Once it arrives at host A will discard the layer 2 header. Host A will then discard the layer 3 header. And finally, host A will receive the data. So that is how a packet will go from host A to host B and back. And this is also another good time to turn it over to the chat. Snakebite, awesome. That's great feedback. I'm glad you've enjoyed it. That's actually the plan or the goal for the entire series, is to explain it in a way that is permanent. But yes, how is all this sitting? Did all this make sense? Oops. Yeah. What do you guys think so far of the router lesson and the content for the router lesson? Nice, awesome. Glad to hear it. Okay. Well, yep, correct, Sarandra, absolutely. Okay, so let me actually show you guys where you guys can get the rest of the videos in this series. If you type in pracnet.net into a web browser, or just go to my website, practicalnetworking.net, you'll come across my blog right here. And then right below my pin post, I think there it is, the networking fundamentals post. If you click that guy, that's where I have a link to every video that I've already created in this series. You can read through the details, right? But this is everything that's already been created. And these are all the lessons that I was referring to. So there's lesson 1. These are the 2 videos for lesson 2, the 2 videos for lesson 3, and the 2 videos for lesson 4. You'll see that right now, lesson 5 is currently in progress. I'm currently creating the content for lesson 5. That's actually the stuff that we've been demoing so far in this live stream, is we've been going through the lesson 5 content. Cool, Akim, that's a great question, and I answer that question in this video. So definitely check out the lesson 2A video right here. I'll go ahead and put this in the description in the chat room. Cool. Now, going back to what I was saying. What we've looked at so far is everything that I've already created in lesson 5. The next part of what I would like to teach in this lesson is what I've already said, is having host A send a having host A send a packet to host C. The issue is I still haven't finished the slides. So we can step through it right now with kind of the bare bones versions of the slides, but they're not going to have all the cool text animations that the ones prior just did. So we are going to go through it together just for the sake of teaching it, so I can give you guys the complete picture of what lesson 5 will include. But insofar as what's fully ready to go, it would just be what we've done so far. Surendra, great question. Hopefully by the end of the month. Again, I prefer to take my time and release really high quality content than try and just publish things before they're ready. My plan is that if you watch something of my content, it'll be the last time you need to watch anything related to that concept because you'll understand it so fully. Cool. Now, before we do what's next, how do we feel about everything involved to get a packet from host, to get the packet from host A to B and back? Do you guys all feel good about all the content we discussed so far? Any questions on anything? Any feedback on anything? Do you think anything needs to be different insofar as the content that I've put together? Let's see if my camera works now. Yeah, I don't know. Sorry about all the switching around there. I was hoping to restart the camera, but it doesn't seem like it's working, so let's not worry about it for the rest of the day. Cool. Okay. Well, if all that is sitting well, we can proceed. Again, the animations won't be quite as fluid as they were before. Again, this is all stuff that I'm currently working on. I was literally working on these slides yesterday and today. In any case, we can still step through all the steps together. So host A now has some data that it's trying to send to host C. Host A is going to add a layer 3 header to that data. That layer 3 header is going to include the source IP address of host A, 10.044.9, and the destination IP address of host C, 10.00.7. Sorry, 10.066.7. Then, since host A had already done ARP prior to get a packet to host B, host A already knows the MAC address of the router. So it can create a layer 2 header that includes the MAC address of host A and a destination IP address of EEE1. I like it, Tony. That's totally fair. I hope you're here more for the lesson than for me. Cool. This is what's going to get that data to the router. Now, once the router has it, again, as we've discussed before, it's going to get rid of the old layer 2 header, which is only there to get the packet to the router. And now the router is going to look at its routing table to try and figure out how to deliver this packet. The destination IP address of this packet is 10.066.7. The router has an entry in its routing table for 10.066.7, well, dot anything. It knows it needs to get a packet, rather, it needs to deliver this packet to 10.055.2. Now, R1 can't add another layer 3 header with a destination IP address of 10.055.2. I mean, that would work, but then the router, R2, would think that this data is meant directly for the router. Instead, what R1 is going to try and do is add a layer 2 header. Add a layer 2 header, which will take this to R2. But the problem at the moment, if you look at R1's ARP table, R1 does not have an entry for R2's IP address. So it's going to have to do ARP just like the host did ARP, and just like it did ARP earlier. It's going to send out an ARP broadcast asking for the MAC address of R2. Upon receiving the ARP broadcast, R2 will have learned the ARP entry for R1, and then R2 will send back out the ARP response. That is what's going to teach R1 the ARP entry that correlates to that static route, the ARP entry of R2. Now, R1 can create the layer 2 header, which will take this packet from this NIC to this NIC. And now R2 has the data. R2 again is going to start by discarding the layer 2 header because again, that only existed to get the packet from here to here. And R2, just like any other router, is going to look at the destination IP address to try and figure out where this packet should go next. In this case, the 10.0.66 network should go out R2's left interface. That's this direction. At the moment, R2 doesn't have the mapping, the ARP mapping for host C. So it's going to have to do ARP. So it's going to send out an ARP broadcast asking for the ARP mapping. Host C is going to respond, and that's what's going to allow the router, R2 in this case, to learn the ARP mapping for host C, which will allow router 2, R2, to create the layer 2 header, which will take this packet from this NIC to this NIC. Notice the source was EE4 and the destination was C7C7. That's what will get the packet to C7, rather to host C. Once it gets to host C, oops, I don't have the animations for it. Host C will just discard the layer 2 header, discard the layer 3 header, and then process the data. And those are all the steps to get a packet from host A to host C. Now, if some of this is sounding repetitious, that's a good thing. That means you're learning the underlying functions and rules for what the router does and what the host does and how ARP works. And it absolutely is repetitious, right? Every router is going to work the same way. If it needs a layer 2 header, if it needs a layer 2 address, it's going to do ARP. If it receives a packet, it's going to look at its routing table to figure out where to go with the packet. And hopefully by now, you can see all the steps involved for routers to deliver packets. In the final version of this video, we're going to also do the return traffic, host C back to host A. But again, I haven't finished those slides yet. But that actually wraps up the entire lesson. So there's a question in chat: can a host receive an ARP request, send a malicious MAC address in response? Yeah, it absolutely could. That's known as ARP spoofing. That's why you want to be careful who you let in your network. You only want to let approved hosts in your network, because you can spoof ARP entries for anything within the network. There's also some other defenses you can use to protect against ARP spoofing, but those go somewhat beyond the fundamentals that we're discussing today. Cool. Well, that is actually it. That's all I had for you guys insofar as this lesson. I'm sorry my camera is still not working. Nope. Well, sorry my camera is not working, but normally you would see my face and I'd give you a send-off. We've actually gone longer than I was expecting. It's already an hour and 15. That's totally cool. Hopefully you guys enjoyed that lesson and that preview for what lesson 5 is going to be in the networking fundamentals lessons. Again, to access the networking fundamentals lessons, it's one of the posts on my blog. You can just go to practicalnetworking.net. I think it's the third one down, or just use the search box right here to search for networking fundamentals. All these videos are free. My goal was to teach anybody networking with these videos. I hope you enjoy them. I hope they're useful for you. I hope they become something that gets passed around as the must-watch for anybody in IT. So any sharing you can do of this content would be greatly appreciated if you enjoy and appreciate this type of work. Otherwise, if you are studying for the CCNA, I have all my CCNA related content in one pretty link right here. You can always get to it at this link right here, pracnet.net/. Oh, you're not looking at my screen, are you? Cool. If you go to pracnet.net/CCNA, you'll be taken to a link to all of my CCNA related content. It doesn't cover everything CCNA related, but I sincerely believe what it does cover, it does so in the easiest way possible and the simplest way to learn. So feel free to check it out. All of this is free. All of that is for you. I would greatly appreciate some shares in response if you can. Otherwise, that is all I had for you today. I will now be answering some questions in my Discord server. You can join the Discord server by typing pracnet.net/discord. It should redirect you to an invite link. I'll be in the Discord server for the next 30 minutes answering questions, preferably about anything we just discussed, but also about anything CCNA related if you want to go further than we did today. Otherwise, that is all I had for you guys. I hope you guys enjoyed this live stream. Hope you guys enjoyed the content. And yeah, we'll catch you guys in the next one. Feel free to join in Discord to chat further. Best of luck, everybody. And I am signing off for the day. Again, I'll be in Discord for the next 30 minutes, so come hang out, ask questions, and I'm happy to help.